Alright, these are a little bit tough, but again, it's eliminate theta. So we've just got to figure out what to do with x and y. We want a Cartesian equation. We want to get rid of any thetas. So a lot of the time we're going to be using excuse me, our identities. Like, for example, this one I've got here, and I'm not sure if you can see it. I'm hoping you can. Just like sine squared theta plus cos squared theta equals 1, we've also got 1 plus cot squared theta equals cosec squared theta. It helps, if we can, to be in the same ratio expression. So if I change this x, if I change the cosec squared parts to 1 plus cot squared thetas, and same with the y. So this would be 2 plus 2 cot squared theta plus cot squared theta. And simplify that, I will get 1 plus 3 cot squared thetas. And for my y, I will get 2 plus 3 cot squared theta. Now, if it works out nicely, so you've got the same amount of the weird one, in this case cot squared theta, so there's 3 in each, I can just do something easy, like, for instance, to get rid of that, if I do y minus x, so I've got 3 cot squared, take away 3 cot squared is nothing, and 2 take away 1 is 1. So that's my equation. You can see it doesn't depend on theta. Alright, so that was using the identity 1 plus cot squared theta equals cosec squared theta. Now, it might not always be linear like that, and you'll note that for the second one, there's sines and coses. Sines and coses, I can't really change one to the other because they're not squared at the moment. But it is nice to remember that sine squared plus cos squared equals 1. So what I can do is just have a little look at what sine squared looks like. So I'm going to square the first term. I'm going to double the product and square the last term. I'm going to compare that with y squared. So again, square the first term, double the product, and square the last term. And they look kind of similar-ish. And the other thing you might like to do is think you've got sine squared plus, if I take one of these, sine squared plus cos squared equals 1, then I would only have 8 cos squareds left, and still 6 minus 6 sine theta cos thetas. If I do the same here, I've got a sine squared plus a cos squared is 1, then I would have 3 cos squareds left. I've got positive 4 sine theta cos thetas. Alright, it doesn't look like I'm going to be able to kind of cancel them easily. For example, doing an x squared minus a 2y squared or something like that. I might also need to look at xy. That can come in handy as well. So if I do that, I've got sine squared theta. I've got minus 3 sine theta cos thetas. I've got 2 sine theta cos thetas and minus 6 cos squared thetas. So if I simplify that again, sine squared, if I made this a minus 7, then I could add 1 over here. So sine squared plus cos squared could equal 1. Just to keep it nicely set up like the others, then I could have a minus 7 cos squared theta. Minus 3 plus 2, so I've got a minus sine theta cos theta. Now, can I use a combination of those to get rid of all the cos squareds and the sine coses? And if I look first at the cos squared column here, I've got an 8 plus a 3 and only a minus 7. So can I use 8 and 3, the positives, and the minus 7? So if I double minus 7, I get minus 14. Can I get a 14 out of 8 and 3, for instance? And I can actually do that if I double this one. So if I times everything by 2 there, I get a 14 cos squared theta, and if I times this one by 2, a minus 14 cos squared theta. So I might actually try that, see if that works. So what I'm doing is trying x squared, and I'm adding 2 of the y squareds, and I'm also adding 2 of the xy's. Let's try that out. So this would be a 1 plus a 2 plus a 2, so that's a 5. 8, 9, 10, 11, 12, 13, 14. Okay, so I've got a 14, take away 14 cos squared, that's a 0. So I've got 0 here. And I've got negative 6 of these plus 8, so I've got an extra 2. And then I'm minusing 2, so that's also a 0. Perfect. All right, so now I've gotten rid of all thetas. My equation is just this: x squared plus 2y squared plus 2xy equals 5. And we've eliminated theta. So you have to play around a bit, but it's handy to write them all out and just compare them and see if you can get rid of them, the sine theta, cos theta stuff. All right, let's look at the last one. Now, the last one already gives us, which is very nice of it, it gives us what to do, really. And it says x squared y is our hint, so that's exactly what we're going to do. We're going to have a look at x squared. So I'd get sine squared theta. I would get 2 sine theta cos theta and cos squared theta, and we know that would be 1 plus 2 sine theta cos theta. And I'm looking at y as well, and it wants me to multiply it by y. Okay, so actually I probably should have just gone, will I get rid of that? I might just go, I'll leave it. All right, so remember, you can do things all different ways. So let's have a look at x squared y. So I'm timesing all that by, might write it here, so it's just a bit easier to see. Sine theta cos theta by y, and y is, alright, I write it like this: tan theta plus, and this would be cos theta on sine theta. Should I actually rewrite that as sine theta on cos theta? Alright, so if I do that, I get, I still get my tan theta. So I'm still going to get my tan theta from that one. And I'm still going to get my cot theta from that one. So that's the same as y there. But from this one here, I'm going to get, the coses will cancel, so I'm going to get 2 sine squared theta. And for that one there, the sines will cancel, so we're going to get 2 cos squared theta. Alright, that's nice. So you can see there that this part here will give us 2 lots of sine squared plus cos squared, which is just 2. And this part here is our y. So actually we can change that to y and this to 2. So we do have an equation here. We've got rid of all the thetas. Y plus looks like z. But that is y plus 2. There you go.